Okay, so Happy New Year. Welcome to the year 2023. So I hope you guys enjoy your little festivities for New Year's Eve / New Year's. So I like to ask you guys in the comments, what's your New Year's resolutions? I'll tell you mine. For me, I know it's a pretty generic comment, or rather the resolution's been set like for a lot of people that they want to go back to the gym. But for me, I want to do that, but it's mainly because I actually want to get back into playing basketball. Since it's been like quite a while, or rather some months that I last touched a basketball. And I also have some shoes that I have yet to wear that I really want to wear while, getting my exercise on. So anyway, that's just all I want to say. So hope your resolutions, comes true when it comes to that time. So we'll start off with something that looks a little bit easy of an integral. We have the definite integral from 0 to 1 of arctangent square of x dx. So it looks easy from a glance because, arctangent x on its own, if we actually do the integration behind that, that's pretty straightforward. You just apply, integration by parts, and then whether it be a definite or indefinite, it's easy from there. But we have, the exponent 2 on top of that. So does that make it easy? Well, for one thing for sure is that the IBP, integration by parts, the step is involved in this, procedure. And another thing is that there's actually, when you split this up and divide this even further on how we proceed forward, that there's actually another integral that we're going to have to tackle, but it's actually a lot harder. But we don't have to go too much about it because actually from that result, I've actually proven from a video a long time ago that once we get into that, I'll go into a little bit of detail behind it. So that's pretty much the straightforward on how we're going to calculate something looks like deceivingly easy. So let's actually just start off and start off the year just right. So let's choose our u and our dv. We'll let u simply just be arctangent square of x. So if I just do the differentiation, du is just going to be 2. So just apply the chain rule alongside that. So 2 times arctan of x, and then divided by 1 plus x squared followed with dx. Then if we choose our dv's just, are the easy pickings from there. dv, will let that be dx, and then integrate both sides. So v is going to be x. Now, putting this all together, we'll call our integral that we want to calculate capital I. That's putting everything back together. We have x times arctangent square of x, and then evaluate this from 0 to 1. Then we subtract, and then I'll factor out the 2 from outside of that, and then multiply with our v du of the integral. So we have 2 times the integral from 0 to 1 of x multiplied by arctangent x, and then divided by 1 plus x squared, then multiplied with dx. Okay, so now to put things even to simpler calculations, we know that if I plug in 1 over here, that it means, and that'll yield to pi squared divided by 16. And then if I just plug 0, that's just going to be 0. And then subtract 2 times this integral. I'll just denote this as capital I sub 1. So of course, capital I sub 1 is what we have to calculate over here. So let's actually get to that. So our I sub 1 integral. So of course, that's going to be the integral from 0 to 1 of x multiplied by arctan of x divided by 1 plus x squared dx. It's straightforward to see that we're going to have to apply some u substitution methods here. So in this case, we'll let u be arctangent of x. And also keep in mind, we have an x over here in our integrand, so we'll have to put this back in terms for x to solve on its own. So we'll let that be that x is equal to tangent of u. And I'm actually going to differentiate the first part, so du, and then for to find the dx. So du in this situation will be, this is going to be 1 divided by 1 plus x squared, and then multiply with dx. So we put everything back together. So we're going to have a new integral. So we have, and we're going to have to change our bounds too. So I plug in 0 for x. So that means u is going to be 0. And if I plug in 1, so that means u is going to be pi divided by 4. And then what we'll have now is, now we have plug in u and then multiply with tangent of u du. And then to calculate something like this, we're actually going to have to apply yet some integration by parts again. So we'll let u, and well, I'll actually change the variable notation to something different since we have a u and we've done a v. So this time we'll let this be y. We'll let y equals u. And so differentiate that. I have that dy is going to equal du. And then we'll let dw be tangent of u du. So if I integrate that, so that means dw. So integrating this means you have to apply yet again with some integration by parts. That means w will have to be negative the natural log of cosine of u. Okay, so now with that, we're actually going to put everything back together. So now our new I sub 1 integral rewritten is that for the uv and then vdu, we'll have negative u multiplied by ln of cosine of u, and then we actually evaluate from our bounds from 0 to pi over 4. Then subtract, then we have a minus over here. I'll factor that out. That becomes now a plus. So plus the integral from 0 to pi over 4 of the natural log of cosine of u and then du. And now to continue the evaluation even further, we'll save this on the side for just a second. So focusing on over here, if I plug in pi over 4, so that means I have negative pi over 4, then multiply with ln of cosine of u, which is the square root of 2 divided by 2. And then in other words, and then plug in 0 for over here. That means cosine of 0 is going to be 1, then ln of 1 is 0, then 0 over here. So that's fine on its own. Then if I want to simplify things even further, so the equals, of course, is just to denote this piece. We'll get to this step eventually. So simplify things even further using some natural log properties, we can write this as negative pi divided by 8. So it's simply because it's coming from the square root symbol, so 1/2, and then factor that out from the exponent of ln of 2, and then add this with pi divided by 4, multiply with ln of 2. Okay, so now the question is, how do we evaluate this integral over here? So this is where the result that I mentioned actually comes into play. So ln cosine of u then du. So a video I did a long time ago, probably like 2 years ago, I think, when I was like starting out, is that I actually did the integral from the natural log of sine of x dx up the same bound from 0 to pi over 4. So yes, two completely different integrands, but on the same bound. However, if you actually watch the video, well, if you can choose to, I'll leave that link in the description below and on the cards, that we actually evaluate things such that we take the sum and the difference of both the natural log of cosine of x, we're just saying x in this convention, and the integral of the natural log of sine of x. And then if you actually derive both together, if we have the sum and differences together, that we can actually solve this such that we can actually solve individually for ln of cosine of u and then ln of sine of u. I know I'm getting switching letters, but the meaning stays there. So with this in mind, at the end of the video, well, close towards the end, that we actually solve for by itself, and you can actually put it into like a systems of equation that we can actually solve for the individuals of those integrals on its own, which we plan to do. So from this video, and then I'm just gonna put this arrow over here, just denoting the next steps. So we have that the natural log of, well, first I have to write the integral symbol, that's the important part. We have that the integral from pi over 4 of the natural log of cosine of x, and then dx, we're gonna say x in this situation. Then add this with the integral from 0 to pi. Well, let me actually switch this up because of the convention, specifically the naming, how this was written. So what I had was the natural log of sine of x, then dx. Add this with the integral from pi over 4 of the natural log of cosine of x, dx. The evaluation came to that for the sum of these two is going to lead to negative pi times ln of 2, and then divided by 2. And so another thing is that the second integral of its difference, so 0 to pi over 4 of the natural log of sine of x dx, subtract the integral from 0 to pi divided by 4 of the natural log of cosine of x dx, is simply just equal to negative c, where c is denoted as Catalan's constant. With this in mind, I can actually solve this as a systems of equations. So let me actually we'll call this capital I sub s. And it's actually the same convention I've written in that same video as well. And then we'll call this capital I sub c. Well, the way I drew the brackets is mainly to denote the entire integral, not the integrand. So if we solve this out, so I have I sub s plus I sub c is equal to negative pi ln of 2 divided by 2, and then I sub s minus I sub c is equal to negative c. And if we want to solve for I sub c, aka this integral over here, let's actually solve this as a systems of equation as mentioned. So I'll just multiply a negative 1 to the bottom equation, meaning that this will cancel out the integral or for the natural log of sine of x. And if we actually put this together, we have 2 times I sub c is simply just going to equal the Catalan's constant, then subtract pi ln of 2, then divided by 2. And then if I solve for I sub c by itself, just divide the 2 to both sides, we have that this is just 1/2 times c, and then subtract pi ln of 2 divided by 4. Okay, so then with this situation, we have now that putting things back together, so I sub 1, aka the integral that we're actually trying to calculate over here, and then what we came to the result is over here. So now we have that this is equal to negative pi ln of 2 divided by 8. Add this with pi divided by 4 ln of 2, and then add this with the integral which we solved for. This is plus 1/2 times c, and then subtract pi ln of 2, then divided by 4. Of course, we're going to have some terms that cancel each other out. So we have the pi over 4. Why is this so hard to open? We have the pi over 4, and then the pi over 4 times ln of 2 cancel, so we're actually left with I sub 1 equals negative pi ln of 2 divided by 8 plus 1/2 times Catalan's constant. So now we just put that back into over here, so we have to multiply the 2. So therefore, just to simplify everything out, we have that capital I, which is the integral we want to calculate, is equal to pi squared divided by 16, subtract 2, then times negative pi ln of 2 divided by 8, add this with 1/2 times Catalan's constant, then just multiply the 2. So let's see, that means I have now this is just 1 over 4, then multiply with ln of 2, and then we're just left with plus c. Well, and then distribute that, that's the minus, so that's a plus, and then it becomes a minus after the distribution. So therefore, it just leads down to the final answer of pi squared divided by 16 plus pi divided by 4 times ln of 2, and then add this or subtract with Catalan's constant c, and so therefore that's actually the final answer to this, deceivingly easy, possibly, integral over here. So there we have it. So it's not as easy as you think. In other words, we're gonna actually in the long run. So there we have it, and yeah, that's pretty cool if you ask me.